Hello and welcome. This is chapter 2. Section 7 is the last section in this chapter, and it goes a little bit more detail about when acceleration is not constant. Um, so uniform motion is when acceleration is obviously zero, and the past 3 sections can deal with examples where an acceleration changes, but it changes from one constant value to another constant value. This section deals with accelerations that are actually variable. And the most we can do with accelerations that are variable are set up a general framework. We can't, without knowing more about the problem, we can't say anything specific or derive specific equations. But at the least part, let's start off with this, these two graphs. So we've got a velocity versus time graph of a car as it approaches a maximum speed. This is pretty realistic, even if you're testing performance vehicles. You slam on the brake or slam on the gas right at the beginning, you have a large acceleration. But the thing is that the acceleration will increase the drag force. More motion means more drag. So you have drag going against, the forces that the engine is outputting. And so that's going to lower the acceleration, but it's still speeding up. And so the speed increases, but drag increases, and therefore that lowers the acceleration, but it still speeds up. But that lowers the acceleration, but it still speeds up, and that lowers its acceleration. And you can see the loop that you get into. This is the sorts of graphs that describe it. And then the acceleration, it's going to start at a maximum value and then decrease to perhaps zero if, for instance, like a falling raindrop reaches terminal velocity, or like a hailstone reaches terminal velocity. So we use the full definition of acceleration as the derivative of the velocity v sub s with d v sub s vt, and that is the actual slope of the velocity versus time graph if it's not constant. We can also turn this problem around and say, well, if the acceleration versus time is known, then we can integrate it, and the area of that curve represents the change in velocity in that time interval. And so there's an example here, a very simple example here, where we have a acceleration versus time graph that is variable. We start off with a constant acceleration from 0 to 4 seconds. And then between 4 and 8 seconds, the acceleration goes down to 0. So, before we get into it, what does this motion look like? Well, we're speeding up at a constant rate. So every second, our speed is increasing proportionally, but then our speed kind of trails off. And to be honest, this graph is an attempt to sort of model these car graphs that we just saw of acceleration versus time. And so we can find the area of this curve. Pretty simple. It's just a trapezoid, and find the change in velocity in those 8 seconds. It's pretty clear. What's the slope of the acceleration? What's the slope of the acceleration versus time graph? Well, the first 4 seconds is 0, but between 4 seconds and 8 seconds, it would be the change in acceleration is -4 over a time interval of 4 seconds. And so that slope, that decreasing slope, is -1, and now it'd actually be meters per seconds cubed. We don't ever formally define like a jerk or a quantity with units of meters per second cubed, but that's what that slope is. Now, interestingly enough, the graph continues to 10 seconds. Does the thing change direction? And no, the answer is no. What's going on is that the speed is changing, and then you eventually get to where it's still moving, but the rate of speed is going down. Now we're slowing down. We're still moving in that direction. So it's kind of weird to think of this graph where, we speed up, and then we're still speeding up, but the rate at which we're speeding up is slower, And then eventually, after 8 seconds, we're literally just slowing down, but we're not turning direction yet. Okay. And so, continuing that example. These are the last sections, and of course there are these summary slides in each of these chapters. The final thing that I'd like to mention in this section is that acceleration doesn't necessarily have to be a function of time. Acceleration can be a function of position. Acceleration can be a function of velocity. Acceleration could be a function of all three of them: time, position, and velocity. And when acceleration is a function of one of those quantities, you need to use different techniques. This chapter or this section only covers when you have time acceleration, the acceleration changing in time. Later on in the semester, we'll handle examples where there's acceleration as a function of position, as in like flexible strings and springs, or acceleration as a function of velocity, for instance, drag forces. And so these summary slides are pretty good. This is the end of chapter pages at the end of these chapters. I would encourage you to look over those. It kind of summarizes the models, summarizes the equations, really summarizes all of the chapter sections. So talking about the relationship between the graphs, the integral relationships, the derivative relationships, and even some applications. So that is it for chapter 2. In the next chapters, we'll define vectors and extend motion to 2 dimensions, and then eventually get to forces. And that will be, once we're done with the forces, that'll be the end of the main first part of this course. So thanks for your time, and we'll see you in the next video. Take care.